So conclusion of this first paragraph is that with these conservation laws, you end up with the two classical models. First, the Euler model. The Euler model is for ideal fluids. So for this, you have the incompressibility condition, and you have with constant density the conservation of momentum. And in this conservation of momentum, you take only pressure into account. So what you get is the following equation on the velocity field: dtu plus u dot grad u plus gradient of p over rho equal some volume forcing, but I will take it to be 0. I neglect any, you could add some source term. So that's Euler equation. Rho is a constant, is a given constant. And then the other classical model is the Navier-Stokes equation. Navier-Stokes is for viscous fluids. You take into account viscosity by adding some diffusion, because viscosity creates friction, it dissipates energy, so this is the same with the minus delta U. So you will have, for Navier-Stokes, okay, no, let me look here. Have dtu plus u dot grad u plus pressure gradient minus some viscous term, that's minus mu delta u. And you keep the incompressibility condition. Okay, so that's Navier-Stokes. So again, rho is a given constant, that's a constant density. Mu here is some given coefficient called kinematic viscosity coefficient. And in this problem you have two equations, both in Euler and Navier-Stokes, and you have two unknowns which are the velocity field and the pressure field. So the pressure field is some kind of weird unknown, but I will come back to that. Okay. So here you have the unknowns which are u, the velocity field, and p. And I will come back to that.
I have a stupid question. I don't know what it's true, but P is known as the Lagrange multiplier.
P is exactly like the Lagrange multiplier associated to this. I will really come to that in a few minutes.
And then it's also safe to say that these equations also imply the conservation of energy. So which means that if you use the conservation of energy, you don't get any new equations on this.
Yes, I will come to the energy conservation conservation after that. So of course these are basic models, right? I mean, you neglect compressibility, you say it's incompressible, you neglect variations of density through space, you neglect temperature effects. Okay? So you have, of course, in field mechanics you have much more elaborate models. But okay, these are the most famous, the most classical ones. Okay? So Euler equation is from 1755. First nonlinear PDE ever written. And okay, this is from 19th century with input from many people, not only Navier experts. Okay, so these are the Euler and Navier-Stokes equations. So now, just a word about boundary conditions. So boundary conditions. So let me recall that we denote it by omega the fluid domain. Okay? And there are three classical cases that you want to consider. First case, which is the most realistic one probably, is the case of omega being some bounded domain of Rd. So if you take a domain with a boundary, then you have to add some boundary conditions besides the equations. Okay? And so it depends on the equation that you consider. Either you work with the Euler equation or the Navier-Stokes equation. So for Euler, it's like a hyperbolic problem. So the classical condition is saying that the velocity is tangent to the boundary. So the normal component at the boundary should be 0. It's saying that there is no inflow and outflow. This is impermeability condition. But for Navier-Stokes, you have a parabolic problem. So you can, and that's a natural condition, you can say that the whole velocity is 0 at the boundary. Okay, there is no slip condition. So that's an experimental fact, at least at reasonable scales, that viscous fluids do not slip at the boundary. So this is called the no-slip condition. Okay, so this is the most realistic case of a bounded domain, but for the mathematical analysis, it's useful to get rid of the boundaries sometimes to focus on other issues. So other choices could be the torus, TD, corresponding to periodic boundary conditions. And you could as well take the whole space, Rd. And then we will impose some decay at infinity by proper choice of the functional spaces. Okay, so here you can add some decay. And so actually in most of what will follow, I will take the whole space. Okay, So I will get rid of the boundaries and I will consider ball space. So now you have the equations, you have the boundary conditions. I would like to come back to the role of the pressure here. So, let's see. Role of the pressure. So, Euler form that is closed. How many equations do you have? If we think about scalar PDEs, U has D components, that's D equations, and you have another scalar equation there, so that's D plus 1 scalar equations. For D plus 1 scalar unknowns. U1, UD, E. The D components of the velocity field and P, U1, UD. But the thing is that for each component of the velocity field, you have an evolution equation, you have a dTu. So you take any scalar component, dTu1, dTud, but you have no evolution equation on P. Okay, so in some sense, the gradient of P comes with divergence of U equals 0. And as Ben said, it would be, you can really see this and you can make it rigorous as some kind of Lagrange multiplier associated with this constraint. Okay, but it will take some time to make